To start with a quick question, how many people have ever been frustrated in being hindered by some sort of connectivity failing or inability to get your data as described from your equipment or machinery? Most people? Anybody? So that's where I come in to talk about the Internet of Things. And just as a quick overview, you have all sorts of devices that are going to be connected on the job site, and any physical device that is connected to either a cloud or some sort of through wireless mechanism to represent data is called a cyber-physical system. And the aggregation of the data from these cyber-physical systems, as well as the processing that occurs in the cloud, is what creates a virtual physical feedback loop that is the inherent focus of the Internet of Things. So just an overview of our literature review, considering the state of the Internet of Things right now. There are many, many, many different applications. There's many different types of equipment, from the small, simple sensor nodes for environmental monitoring or personal protective equipment verification or access control on the site, to the very complex like point clouds that are developed from photogrammetry or laser scanning, as well as the building information model collaboration tools, even further being extended to augmented reality and virtual reality for the site. And so what I'm going to talk about is some of the major problems that we face within IoT rollout, namely labor, power, complexity, interoperability, usability, and cost. And as you can see by the arrows, these problems have emergent solutions that are attempting to address them variably. With labor, we'll talk about a different workforce that's going to be needed to offset the current workforce and thereby utilize the technology in place of the human aspect. Power has the potential for many different energy harvesting mechanisms that I will overview briefly. Complexity is helped by artificial intelligence. Interoperability is being solved both by standardization efforts and the open source paradigm, which I will discuss further later. And usability really comes down to, are the devices rugged enough, and is the end user willing to accept the use of whatever equipment is being put into the field. So after this paper was published, I went out into the field and I spoke to well over 100 construction professionals of all different job type, different roles within the company, even beyond construction with a lot of the other partners that are external to a specific contractor, such as financial institutions that will fund the building of a project, or the manufacturers of the devices involved. So what we found first through literature review and through field interviews was that the number one problem, particularly in the United States, with construction is labor. The lack of labor, the lack of skilled labor, and the inability to get the amount of people we need to do the job on the job site. And construction is inherently known for being not a very productive industry when compared to most others. So like I said, the biggest problem is labor and productivity, but when you consider that the way that contractors approach solving the labor issue is either through incentivization or technology, you have to recognize that incentivization is expensive. As mentioned previously from one of our colleagues, that if you think about an IT salary being $100,000 a year, how much equipment can you buy with $100,000? How much data can you stream? How many monthly services can you get with $100,000? That's a lot. And even then, if you incentivize workers to your job site through financial bonuses or through other perks, that doesn't help the fact that there are certain things that they don't know. It doesn't make people more skilled. So technology comes in to offset that. Technology and computers comparatively are efficient, cheap, and they're also incredibly accurate and precise and not subject to the human error. But when the connectivity fails, the data can be lost, data can be damaged, the data can be faulty, and this is a big hindrance. So the biggest problem with technology in construction is actually going to be the network. And as an example, even the new football stadium in downtown Jacksonville that was being constructed, well, it's actually a training facility. The network was so bad within the middle of the city on that project with dozens of routers everywhere that the field crew actually had to take all of their data to the office and upload it that way. So again, if you think about construction and that not all projects inherently have power infrastructure, how can you expect them to have connectivity infrastructure? So you can't talk about the Internet of Things without first addressing power and making sure that there is power on the job site. Otherwise, you won't have the ability to get your data out. You won't have the ability to wirelessly transmit. And then the other problem that follows that up is complexity. And complexity takes really 3 different forms. First, when you think about the job site, as I pictured before, each of these parties with each of these different little wireless bubbles showing above their head or above the equipment, those are, when you think about it in construction, belong to different parties. You know, each one of them could be a different trade. Each one of them is a different piece of an organization. It's not a very coherent environment. Furthermore, the materials, equipment, and the environment themselves are in constant flux on a construction site. Everything's moving everywhere. This creates a lot of problems with interference and so forth. And beyond that, the business of construction it's got a complex structure as well. And when you think about the fact that the business requirements of the contractor are different from the requirements of who funds the project. So that creates a discord that also prevents Internet of Things being used properly. But most importantly, the complexity that I'm going to talk about a little bit further is within the network and how complex just developing the network can be based off of the various regions in the frequency spectrum that you can use, as well as the different hardware, software, and protocols that are used. And so a lot of people ask me about, hey, well, you know, 4G and 5G, you know, they promise a lot of things. Are they not good enough? And really, when you think about the upstream, and by upstream I mean towards the top of this image, there are things that work. You know, if you do get to the office, you can get your point cloud up to the cloud pretty easily. And that allows for data analytics, that allows for artificial intelligence, that allows for BIM collaboration and digital twin. But really, when you look down at the edge computing and even lower to the physical devices, there are a lot of interconnections that have to be addressed in almost an application-specific context, kind of one-offs, and that's a difficulty that we're going to have to discuss. So here's just another reference to the complexity of the networks. Within 4G alone, in the United States and in Europe, we have both narrowband IoT and long-term evolution for machines, which is, but depending on where you are, you're going to have to know which part of the 4G spectrum you're using and what your cellular providers offer. And they talk all this about 5G and how 5G is going to provide a bunch of offerings and solutions as well. But even within 5G, there's your enhanced mobile broadband, your ultra-reliable low latency communications, and your massive machine type communications. And so you have to really know what you're using. But then once the license spectrum fails and you can't use the cellular grid, a lot of what occurs is putting in this unlicensed spectrum and utilizing the various protocols shown here to create an ad hoc network that's more usable for your job site. And just for future availability, from what I've learned in our literature review, is that the systems in bold, I think, have the most promise, or the protocols in bold have the most promise for the future. And so why do so many protocols exist, particularly within the low-rate wireless personal area networks that you see by 802.15.4 in the IEEE? It's because each of these protocols has a different power consumption, a different transmission range, a different channel access method type. They have different network types. The architecture of them can change. The packet and frame size can change based off of the headers that are put to say what device is speaking, and that creates an issue with interoperability. Furthermore, other considerations that you need to think about in network deployment are cybersecurity, quality of service, bandwidth, throughput, robustness, ruggedness, and so forth. And even further, talking about interoperability, when people think of a sensor node, you have to realize that there are many, many components to a sensor node. There's the power module, electronically speaking, you know, you have energy harvesting potential, you have conversion, you have the local memory cache, and not all of these devices are going to come from the same manufacturer. So if there isn't some sort of method to make sure that these are interoperating properly with one another, you can run into a lot of issues and spend a lot of time there. And finally, when talking about ruggedness, here's just an example. If you look at the laptop on the left that's non-rugged, it's half as expensive as the laptop on the right that is ruggedized, and that's even with a newer processor with twice as much RAM. And so it's just an issue that you have to address early on in the cycle, is that if you're going to ruggedize your equipment, you can't just look at the costs of them inherently you have to also look at what is the cost to make sure that that equipment's robust. So the first solution that we propose is really a new workforce needs to be established. There needs to be a new title for the person that is going to be that IoT integrator for the job site. And just as a quick example, this is one project that I was hired for during the pandemic for a company that was trying to get ambient environmental monitoring. And so they used their own virtual design coordination department to try to R&D their own sensors into the field. And what they ended up having to do was hardwire every single device. And they tried to print their own housings, and it just didn't work. The housings failed, the hardwire became trip hazards, and it was just incredibly congested. So we went in and made a battery-powered, well, I personally and then one other guy that was hired by the company went in and made this battery-powered system that you see on the right for access control and for environmental monitoring. It took us a couple months, and so with the knowledge that we had as a computer programmer, as an electrical engineer, it really helped the company. Talking about energy harvesting as well, most people just think of like solar, but when you think about it, if you look at the bottom left and you think about just a microprocessor, microcontroller, what they take to run, what the sensors take to transmit their data, there's lots of different energy harvesting mechanisms, whether it's electromagnetic or piezoelectric, electrostatic, and so forth. So this is where artificial intelligence can come in to help as a solution as well. When you think about this Venn diagram here, you have trade-offs between cost, power consumption, power generation, and data rate or wireless range, and all of them kind of pull towards one of these bubbles. And if you look at the next stage in, this is why. Because if you think about reducing power consumption, it's inversely related to the cost, because if you're going to get a more optimal device, a more efficient device, it's going to cost more. In the top middle bubble, if you think about more sophisticated equipment, just like I showed on the previous slide, if you get up there to the actual power tools or your Boston Dynamics robotic dog or your UAV, those things you can't really harvest energy for. You actually have to go back and plug them in every day. So that's something to consider. And then also, the greater the data rate, the greater the power consumption. That's kind of a given. And within the internal bubbles here, outside of artificial intelligence and machine learning, you see the energy storage, power cycling, low power protocols, and alpha transceivers. There are great groups of researchers working on all these sub-devices. And then considering interoperability, and you really have to think, this being a European conference and me coming from the United States, I really have to thank Europe for its paving the way and the efforts in interoperability and standardization. And you see what this is doing by creating these alliances is it's really forcing a lot of these manufacturers of electronics to focus on creating products that work with one another. Further considering interoperability, there's the open source paradigm. This project was published by the Association of Computing and Machinery after this paper that I wrote for EC3 was published. But we wrote a program in Dart using the Flutter GUI framework, and all of this is hosted on GitHub if anybody wants to see it. But protocol buffers helped with interoperability, and WebSockets help with power consumption. But then back to the beginning, considering your new workforce again, even though we could use existing code and existing libraries online to get these devices of disparate manufacturer to work with one another, there was a calibration issue in that there was almost a 10-degree centigrade difference between what resulted from the devices naturally without any calibration, even though they were on the exact same environment. And furthermore, you need to have somebody that understands how to parse that open source code as well. So in conclusion, considering the interrelatedness between connectivity, energy, hardware, software, and human requirements in the Internet of Things, we understand that ruggedness is expensive, but in construction it will always be necessary. This should be thought of forefront. A new workforce should be established because of the technical issues and how many of them are going to exist within all leverage devices in the Internet of Things. There is that issue with the power bubble that we talked about, but the more that energy harvesting technologies become engineered to a higher degree of efficiency, the more they're going to be able to be utilized to offset our need on the power grid. And furthermore, artificial intelligence will help in this optimization. Finally, standardization efforts have been made, and this is a great leap forward, so we can utilize that as leverage as practitioners. And finally, as more coherency evolves, future research is going to be required to evaluate these network systems as a whole. When you consider how to get your robots on site, how to get your UAVs on site, how to get your simple sensor data on site, how to get your iPads walking around on site, all of these are going to require different levels of the spectrum. You're going to be able to utilize the different potentials of each of them to actually develop a successful Internet of Things network. that's all. So if anybody has any questions.